Hello, thank you. So I'm going to talk about Mysticeti today, which is a Byzantine fault-tolerant consensus protocol. It's a consensus protocol developed in a company where I work, Myston Labs. I'm not the only author. You can see, like, if you go to the paper, you can see quite a few people contributed to this work. Let's see. Oh, thank you. Just briefly, like, I'm not going to go over this, but kind of knowing those concepts would sort of help to understand. I will speak a little bit about the history, sort of how did we come to this consensus protocol, and also what consensus protocol is and how it's used in a blockchain. So Mysticeti is from a family of so-called proof-of-stake consensus protocol, and they operate in a setting where we have a predefined list of validators, so like blockchain nodes. We obviously tolerate network and machine failures as any consensus protocol, but Byzantine fault tolerance also means that up to a third of those nodes can run arbitrary code, including the try to intentionally subvert the protocol. But at least 2/3 of the nodes behave according to the protocol. And the goal of this proof-of-stake consensus is so that all the correct validators, all the validators that run correct protocol eventually agree on the same state. And state can be different things depending on how I use consensus protocol. Something like Ethereum, for example, agrees on both transaction and execution result. But in our case, we only agree on the list of transactions, and execution happens after the consensus protocol. And if we go a little bit historical overview, the first iterations of Byzantine fault-tolerant protocol, I call them like traditional consensus in the slides. They are proposal-based approach, so they there is a leader on every round, and leader proposes some transactions, and they communicate with other nodes to commit the proposal. This approach is good at have like a very decent leader commit latency. So if I am correct leader, I have a fairly low latency to commit my proposal. But the drawback is that this protocol only commits transactions from the leader. The protocol itself doesn't talk about this red part in this transaction finality, which is how does leader learn about transaction. And that's something that as a user of blockchain, you actually care about. So you don't just need leader commit to be low, you actually want your transaction to commit fast. And mempool is a separate kind of piece of blockchain that would take care of how to deliver transaction to the leader. And as you can imagine, like this mempool kind of is important for like overall latency. So the next sort of attempts to make kind of high throughput, low latency blockchains would try to take like traditional consensus like hot stuff and then pair it with some mempool, which is like efficiently and allows to like distribute a lot of transactions. And one of the first, not necessarily the first, but one of the attempts that sort of I want to mention is Narvo mempool. It creates so-called DAG, directed cyclic graph. And essentially, like the DAG contains of things like those are transactions I want to add to the DAG, and those are other blocks from other validators I've seen. And so at this point, sort of to answer what does consensus commit, it commit the hash of this, like one of the nodes of this DAG-based mempool. And using this technique allows to scale throughput very high. You can get like 100,000 or more transactions per second. But it's two different systems, so the latency of transaction basically, like you need to first propagate it through mempool and then commit it through some different consensus protocol. So the next observation here is that you actually don't need a separate consensus protocol. So once you have this DAG mempool, you actually can interpret this DAG and you can derive the sort of order from this DAG. And so this allows to sort of remove the second part, and you can, like, there's some additional restrictions you need to add to the DAG, but essentially, like, you can have this like Narvo Busher consensus protocol that just have the mempool and consensus running at the same time. It has very high throughput. It does have a very high latency as well. So, like, even though it like can give you like 200,000 transactions per second, the latency is worse than traditional consensus protocol. And so the paper or the consensus protocol I'm presenting today is a Mysticeti. It's a consensus protocol that essentially have a very high throughput, but also it have a very low finality time. It does both work, it does both mempool and consensus. And the way it achieves low latency compared to previous work, Narvo, it uses feature called uncertified DAG. And specifically, it means that every element in this graph is easier to make in a sense. So you can see that only half round trip needed to make element, and in Narvo you need like one half round trip. The reason you need 1.5 round trip in Narvo is because it allows to certify, and this removes certain Byzantine scenarios. And in Mysticeti, those Byzantine scenarios are possible, so consensus protocol needs to sort of handle them. This means that we need more rounds to make a commit, like we need 3 rounds instead of 2 rounds for Narvo, but overall, like the math kind of makes a lower latency, so you do need, overall you do commit faster with this approach. It have a very high TPS of DAG-based mempool protocol. It have a very low transaction commit, which is pretty much the same as you will get with traditional consensus without including even mempool time. It have a very simple networking code. It does have a very fairly more complicated kind of code to derive order from the DAG because you need to handle all the new kind of use cases coming from uncertified DAG usage. So TLDR is like regular traditional like proposal-based consensus, doesn't have mempool, but have very good latency. Throughput usually is low, like because like kind of how this is implemented typically. And a DAG-based consensus traditionally had a very high throughput, but very high latency as well. And Mysticeti does both fairly well. Like it have like up to 500,000 transactions per second, and you can even push it higher. And it achieves very small latency, both by using uncertified DAG and some other techniques. And in addition to this, Mysticeti also have fastpass, which I'll talk a little bit later, but essentially like a sub-protocol on top of Mysticeti, which allows to commit some transactions even faster before consensus. We have implementation for this, obviously, some details, it's written in Rust. The entire protocol, as I said, the networking part is very simple. It's literally like one RPC, which is I connect to other nodes and just ask the node, like, can you just give me your blocks? And like I send the blocks to the nodes that connected to me. The network is fairly simple. It's just like TCP socket between like different nodes. We use async IO to talk to the sockets. The consensus code itself is asynchronous to avoid bugs of not dealing with like asynchronous code and all. We use ED25519 signatures. We also use a val-based storage instead of RocksDB to sort of reduce write amplification. Basically, when you have a very high throughput, your actually disk started becoming bottleneck, even if it's a modern SSD. And we do test this protocol in a real cluster, so we set up like for the test for the graph you see on the next slide. We set up like cluster of 100 or more nodes, and we distribute them across the world, including like Asia, Europe, United States, Australia. So this is like from a test performance. So like as you can see, like it compares to hot stuff, which is like one of the traditional consensus protocol, Narvo hot stuff, which is a mix of DAG-based mempool and hot stuff. Bullshark, which is like previous generation of DAG-based protocol, and Mysticeti-C is the protocol that I'm presenting today. And you can see it kind of have a low latency, and it kind of goes, latency does go up over like higher TPS just because implementation is not perfect, but you still get like sub-second latency with like up to like 300,000 transactions per second, which is I think pretty cool. In terms of practical application, like this is not just a theoretical work, it's actually used in a real world blockchain. So SUI is a layer 1 blockchain which exists today. It's initially launched with a Narvo Bullshark consensus protocol in May 2023, and pretty much the next month after it's launched, we started working on Mysticeti, which is a new consensus protocol. It actually fully migrated to Mysticeti consensus protocol a few months ago, like in fall 2024, and since then, Mysticeti worked pretty well. So it's, I think like not many blockchains actually like switch between consensus protocol while live. So this is on its own pretty interesting. This is what happens with SUI like finality when the switch have happened. So you can see that with narrow bush arc, this is a main graph from a main net. It was 2 seconds, like slightly under 2 seconds with narrow bush arc, and became 400 milliseconds with Mysticeti. So as you can see, this is like kind of works decently well in production, I would say. Another thing to mention is that Mysticeti graph itself, like the same way as I earlier mentioned, in a bull shark, it started as a mempool, but you could use the graph to derive consensus. In Mysticeti, you can use this DAG to derive other, like basically you can make protocols on top of this DAG. For example, Mysticeti has a variant called Mysticeti FastPass. It combines some findings from some previous papers, which called FastPay, and it allows to change, like for certain blockchains, you can leverage this Mysticeti FastPass to commit transaction even faster if you allow users to make transactions where they, well, without going into too much in details, like it's not the general, this optimization does not work always, but you can kind of leverage this protocol to make this like FastPass optimization. And specifically for this optimization, we didn't even need any new RPC, so you basically just add more metadata to blocks in order to implement like an additional protocol on top of this Mysticeti DAG. Yeah, and that's all I have. Thank you.
So any questions? This last paper. Okay, just one general question. So you mentioned your implement system based on Rust. So there's any reasons why you use Rust to implement the system? How about other?
Sorry, can you repeat the question? Sorry.
You implement the system use the Rust language. Yeah.
Yeah.
So there's any reasons you choose Rust? Yeah.
So actually, most of modern blockchain uses Rust. Yeah, there are like a lot of, I would say, good reasons. So previously, I think Go was used a lot. Go, like Rust is just better than Go. It's a compiled language. It have good type safety. It allows you to write a performant code. It's much easier than, let's say, C++. So it's pretty nice language. I actually recommend it. It's like, I think, the best language out there.
Okay, thank you. Okay.